Good morning and good afternoon, everyone. My name is Madan Raj. My matrix number is CD230304. Thank you for taking the time to listen to our presentation today. We are a group of engineering students presenting on manufacturing process analysis, automotive, engine, piston. This is a comparative study between two major manufacturing methods used in the automotive industry: gravity die casting and hot forging. On the next few minutes, we will explore how pistons are designed, manufactured using these two different processes, and which method is best suited for different application considering economic, environmental, and social factors. Let's dive in. Hello everyone. Let me introduce our team. Firstly, we have Kaushika Nair, Analaki BK7. His matrix number is CD230167. Next, we have myself, which is Madan Raj, Analaki second. My matrix number is CD230304. And next, we have Thanasiran Analaki Ravi. His matrix number is CD230093. And next, we have Puvesh Verma Analaki Vishwa Bharati. His matrix number is CD230312. And finally, we have Loka Ganesan Analaki Krishnan. His matrix number is CD230032. And next, my fellow friend will talk about the piston.
Hi, my name is Thanasiran Analaki Ravi and my matrix number is CD230093. Introduction: What is a piston? Definition: A piston is a crucial part of an internal combustion engine. What does it do? A piston is a movable piece that sits inside the cylinder of an engine. It receives the explosive force from burning fuel and gas and converts that energy into mechanical motion that powers your car. Why it is so important? Piston operates under extremely harsh conditions. They experience high cycle temperature exceeding 300 degrees Celsius, high combustion pressure, over 10 megapascals in modern diesel engines, constant motion moving up and down thousands of times per minute. Because of this extreme condition, piston must be made from special materials. Modern pistons are made from aluminum silicon alloys instead of cast iron because they are lighter, reducing engine weight and improving fuel efficiency, stronger high strength to weight ratio, better at conducting heat, preventing overheating, and more wear resistant. Piston design and specification. Now let's look at the detailed design of a piston. As you can see in this technical drawing, a piston has several key components. The crown or head. This is the top surface that directly faces the combustion. Its shape controls the compression ratio and fuel air mixing. The ring belt. This is where the piston rings sit in grooves. These rings seal the combustion chamber and control all consumption. This area experiences significant wear from friction. The skirt. This is the lower cylindrical section that guides the piston up and down inside the cylindrical ball. Modern pistons often have special coatings to reduce friction. The pin bore or boss. This is the hole where the gut pin connects the piston to connecting rod, which transfers the power to the crankshaft. Dimension: for our study, we selected a standard 2.0 liter naturally aspirated engine. Piston bore diameter 86 mm, compression height 32.5 mm, total height 58 mm, pin bore diameter 22 mm. Material: the material is aluminum silicon alloy, specifically known as AC8A. Density 2.7 grams per cubic centimeter, very light. Melting point 570 to 600 degrees Celsius, must withstand combustion heat. Thermal conductivity 120 to 150 watts per meter Kelvin. Excellent heat transfer. Hardness 100 to 130 HB, resistant wear in grooves. Thermal expansion very low. Prevent sizing in the cylinder.
Hello guys, my name is Piston and my matrix number is CD230312, and today I'm going to explain about the manufacturing manufacturing problem statement. So first of all, the piston manufacturing industry faces four key challenges. First of all is high energy consumption. Casting requires 700 degrees Celsius melting, and forging needs heavy presses. Both create significant carbon footprint. Second is material waste. Casting defects and machining scrap require recycling, which uses more energy. Third, energy assets. Improper disposal of lubricant and cutting liquids damages the ecosystem. And fourth is recyclability issues, which is allowing element complicate aluminium recycling causing down cycle. So our goal is find the manufacturing method that balance performance, economy, and sustainable. So for the process A, gravity die casting. So gravity die casting is the most common method for mass production piston. The process is mold prep. Steel dies are preheated to 200 to 300 degrees Celsius and coated with release agent. Second, melting aluminum is melted at 700 to 750 degrees Celsius, flux and degassed to remove impurities. Third, pouring molten metals flows into the die under gravity, no high pressure injections. Fourth is solidification, metal cools and solidify in the mold. Fifth is ejection. Automated pins ejects the solid piston. The sixth is trimming. Excess metals runners rises is removed. And seventh is heat treatment. T6 treatment increases hardens and strength. Eight is machining. CNC finishes the piston to precise tolerance. And key advantages is cost effective for mass production and creates complex shape like cooling galleries and internal cavities, and 100% in high house recycling. All waste is immediately remelted, and the last is fast production with rapid solidification. So that's all from me, and the next slide will be presented by my friends.
Good day to doctor and to my fellow friends. My name is Loga Ganesan and my matrix number is CE220032. Now, for my part, I am going to present about the process B, which is hot fogging. So the steps for the hot fogging is billet preparation, preheat via induction, die lubrication, pressing, flash trimming, heat treatment and precision machining, which is fully described in our report and as well as slide here. And also the key advantages of heat forging is superior strength through grain alignment, better fatigue resistance, less material waste, which we could save more material from unnecessary wastage, and also ideal for high performance and heavy applications. Limitations for this hot forging process is high energy consumption, cannot easily create internal halos or cooling galleries, requires more complex machining such as valve, release, etc., and also higher initial tool equipment cost. And next is process comparison, which is technical performance between casting and forging. As for primary application, casting requires mass market cars, while forging is high performance and heavy duty process. Material efficiency wise, casting is more efficient compared to forging because forging's material efficiency is at medium level. Energy consumption as for casting is also higher than forging. Tooling cost for casting is moderate, which is below than forging, which is very high. Production speed casting is also outscored forging, which is casting process is very faster than forging. Part strength for casting is good, isotropic. For forging is excellent, which is directional. And also geometric complexity for casting is high capability. It is more capable compared to forging, which is limited. Thank you.
Economical and sustainability impact. Economically, casting is best for mass production. It delivers lower per unit cost, fast output, and in-house recycling that saves materials. Forging suits specific parts, which higher equipment and per unit cost, but durability justifies the expenses. On sustainability, casting reduces waste through immediate recycling, while forging consumes less energy thanks to lower melting temperatures and produces stronger, longer lasting parts. In short, for high volume production above 10,000 units, casting is more economical for racing engines or heavy trucks. Forging strength makes the higher cost worthwhile. Now, let's move from economics to workplace impact. From a social perspective, worker safety is critical in both processes. Casting involves risk from molten aluminum, while forging brings noise and vibration. Both demand strict protective measures. Labor is shifting from manual work to skilled technicians who maintain machines and program CNC systems, creating better opportunities. For consumers, forged pistons offer higher safety margins for extreme driving, while cast pistons remain reliable and affordable for everyday use. The choice balances safety and affordability.
Now let's talk about the conclusion and recommendations. No single best process choice depends on application. 2. Casting is the winner of mass market vehicles. Lower cost, excellent in housing recycling, proven reliability for normal conditions. 3. Forging is required for high performance applications. Superior strength and durability, better safety margins, essentially for racing and heavy duty engines. 4. Both processes are improving, which is forging, which is energy efficient induction heating, casting, increased recycled aluminum use, both better coolant recycling. The recommendation I would prefer is the industry should continue using the both processes because they efficiently serve different market segments. The engineering challenge is to continuously improve both for better sustainability, safety and efficiency. Choose casting for affordability, choose forging for performance. That's it from me. Thank you very much for your attention. We hope this presentation has given you a clear understanding of how pistons are manufactured, the trade-offs between different processes and why the automotive industry uses casting and forging. Manufacturing is a complex field where engineering, economics, environment and society all intersect. These decisions affect everything from vehicle affordability to worker safety to environmental impact. We have enjoyed researching and presenting this project, and we hope you found it informative and interesting. Thank you very much from our group.